Hey everybody, let's talk about precipitate formation. So the question we're addressing here is, if I mix two aqueous solutions, am I going to see a solid form? And in order for us to address this, it's going to be all about Q, and it's Q for that solid. So what you're going to do is you're going to identify what solid might actually form, that might be insoluble. And once you've identified that potentially insoluble solid, then you're going to write the dissolution equation and the equilibrium constant for it. And then what you're going to do is you're going to say, well, what are my concentration of ions? And you are going to plug those values in to your reaction quotient, which, remember, has the same form as your equilibrium constant, where you have the concentration of your products, in this case the ions, over the concentration of the reactants, all raised to their coefficients. And then you'll compare Q to the equilibrium constant value, to KSP, for that solid. If Q is greater than K, you have more products, and remember, these products are the ions, than you would find at equilibrium. And so in order to achieve equilibrium, some of those ions are going to need to become the solid. And so what you have is you have a precipitate. Some of the ions that were in solution are forming a solid. If, on the other hand, you have the value of Q is equal to K, we say you are just at the point of precipitation. You'll just start seeing solid form. You're actually at equilibrium. On the other hand, if Q is less than K, you don't have as many ions as you could in solution, and so no solid will form. In terms of words we could use to describe the solutions at these different situations, if Q is less than K, we say that that solution is unsaturated. You could actually add more ions, and they would be able to stay dissolved. If Q is equal to K, we have a saturated solution. And if Q is greater than K, we're beyond the point of saturation. And so you're actually going to precipitate form until you reach and return to that saturated solution. Let's take a look at an example problem that you might come across. If I have a solution that contains some silver ions and some lead ions, and I start adding sodium iodide, dropping it in, the question is, what solid is going to precipitate first? Silver iodide, which will form a slightly soluble solid, or lead iodide. When I look at the KSP values, my gut tells me that the silver iodide is less soluble, so that's probably going to be the first one. But since the lead iodide has a subscript of 2 on the iodine, the concentration of iodide is going to be squared in its KSP expression, and so that might impact things. So let's figure out which of these is going to precipitate first, and let's do it mathematically, because that'll also answer the second half of the question, which says to specify the concentration of the iodide needed to begin precipitation. When you have a problem, the important thing is to start with the dissolution equation for each of the possible solids you might form. So in this case, that is silver iodide and lead iodide. I do want to make sure I'm writing my KSP expressions. And then if you'll notice, you know the value for KSP for silver iodide, and you know the concentration of silver. So we only have one unknown, and so we can plug those values in and solve for the concentration of iodide that would be found at equilibrium. That's the point where precipitation is just going to start, because we're just going to start having some solid form. I can do the same thing with the lead. So for this one, I divided 7.9 times 10 to the negative 9th by 1.5 times 10 to the negative 3rd, and then took the square root to find the concentration of iodine necessary to cause precipitation. And if you look at these two values, you'll notice that the concentration of iodide necessary to start precipitating, so to reach equilibrium, and therefore start the precipitation for silver iodide is much smaller than that for the lead iodide. So this is going to precipitate first, and the concentration of iodine necessary to do so is 4.2 times 10 to the negative 13th molar. You'll have to add a lot more iodide before you start precipitating the lead iodide.